Hello and welcome everyone to this year's DesignFest. I am Meltem Gürel, the Dean of the Faculty of Architecture at Yaşar University. This year, we continue to explore the concept of boundaries under the theme of circulating boundaries. Our theme suggests the idea of applying circular design principles to the built environment, as well as considering its social and cultural aspects. The festival intends to explore different perspectives of the theme by bringing together academia and practice in a variety of events. These events include seminars, a workshop, and a competition, which are open to the participation of students, academicians, and professionals from all design fields. In the next few days, we will have an opportunity to listen to distinguished scholars and professionals addressing different perspectives of circulating boundaries. This is a hybrid event with online and face-to-face meetings. Before we start with our first online seminar, I would like to extend my sincere appreciation to a number of people, to our Vice Dean, Zeynep Sevinç Karcı, for her coordination, and our organizing team, Arzu Cilasun Kunduracı, Sergio Todanio, Matthew Pedargana, and research assistants Müge Sever, Selin Güngör, Ömercan Bakan, and Ecenur Kızılörenli. Also, to our media and graphics team, İpek Ek, and research assistants Begüm Önal, Özüm Karadağ, İrem Deniz Akçam, Deniz Engin, and Duhan Ölmez for their valuable effort in making this event possible. Finally, I would very much like to thank to all of our contributors and participants for sharing the DesignFest with us. That said, I would like to invite Mauricio Gabriel Morales Beltran as the moderator to introduce our keynote speaker, Elma DURMISEVIC. Thank you and enjoy.
Thank you very much, Meltem. I would like to introduce our first guest, Dr. Elma DURMISEVIC. Is the founder of 4D Architects, an architectural office based on Amsterdam. The aim of this office is to contribute to the practice and theory of sustainable design and construction and promote the design of transformable structures. She is also the founder of the European Laboratory for Green Transformable Buildings, GTB Lab in short, a unique initiative that aims at introducing a systematic shift in the building sector, a new philosophy where waste is considered a design error. She is involved in the project BAM, Buildings as Material Banks, which includes 15 partners from 7 European countries working together with one mission, enabling a system shift in the building sector towards new standards and regulations for circular buildings in Europe. Last but not least, she is currently involved in the Digital Deconstruction Initiative, an interregional project in which a digital support platform is developed to enable circular deconstruction. Doctored by Delft University of Technology in 2006, with her thesis, Transformable Building Structures, she introduced many concepts that later will become key aspects of the circular economy, especially the notion of design for disassembly. Dr. Elma DURMISEVIC has been a guest lecturer at a number of universities. She has several publications in the field of circular economy, digital deconstruction, reuse potential, and reversible building design, among others. The Faculty of Architecture of Yaşar University is proud to count on her talk to start our DesignFest. Dear Elma, the floor is all yours.
Thank you very much. It's really a pleasure to be here. And thank you very much for the invitation. I found the concept of this festival really great. Reminds me on also some initiatives we started in Europe, really bringing different stakeholders together, creative industry together around the subject of very serious subject, and which I will also address in my talk today on how do we make a transition towards a more resilient design of more resilient built environment and more effective use of resources on our planet, which obviously is becoming more and more evident that there is an urgency on that level. So I will be talking about a new approach in design, which I called reversible building design. And we'll address also some tools, as Maurizio mentioned. I've been working in this field for more than 20 years and developed within a number of European projects, number of tools that can help us to design buildings in a more circular way, but also to measure the performance of buildings, because we are creating a new world, which I like to call new reconfigurable world. That means that we need to develop a performance measurement system in order to know how to progress and when are we reaching this new world. The main driving force behind everything I will be talking about is definitely the great issue that we are feeling actually on a daily basis now with the climate change, but also I have to say the latest wars that we are witnessing today, which are very much also about resources and how they impact the economic systems. So it's very much how do we deal with the life support system on our planet, the environmental system, which gives us the clean water and oxygen, food to eat, knowing that the way that we have started to use these resources and the way how we process them into a built environment created negative impacts on the whole ecosystem of the planet, bringing us to the question where we are now and what is the sustainability factor of the things that we've been doing. And I think we all agree these days that this sustainability factor of the approach of the economy of 20th century is behind us, that it is not sustainable, being primarily focused on one linear approach to a use of resources. On the other hand, when we look into the way how these resources were used to form cities and built environment, there's also a lot to be done on the shifts in our approach, how we create cities and buildings within cities. Obviously, now we deal with the overpopulated cities, and the shifts of population towards urban environments will increase even more, but the negative impacts of these tons of concrete and asphalt that are creating city structures which are not absorbing water, which are not producing clean water and clean air, becoming devastated for living in them in general, but also on the planet. So the key question is where we are now with this linear economy, which is based on taking, resourcing, making products and throwing them away, creating waste. The linear economy, which is also focusing on the industries heavily based on fossil fuel energy sources. Knowing that the impacts of this kind of approach to our industrialization, which did brought us really significant improvements in quality of life, but at the same time brought us kind of inhabitable planet. And if we want to provide some quality of life for future generation, there is definitely work to be done. Next to that, when we talk about then physical parts of the built environment and really resources which go into products that we use, but also buildings and cities. It is very important to have this map in mind, which is presenting a resource footprint of countries produced by the World Bank on a yearly basis. And what it tells us is basically how much resources is being used per country per year, compared to the resources that these countries have at the disposal per year. What you see here is a different color scheme from 1961, when the planet was more green. That means that countries had more resources at their disposal than they were consuming per year. And this color coding started to shift towards more red in 2014. Almost half of the planet was turning more to the dark red. These red countries implicate that they consume on average 4 to 5 times more resources per year than they have at their disposal. That means that they are heavily dependent on the countries which are still green, but these greens are also becoming less and less green. And that is actually very, very well implicating the issue that I want to talk about when we talk about circular economy and circularity, and how do we introduce circular concepts in construction and why. It is very much about the way how we treat resources in all of our products. And as I showed in previous slides, the linear approach to the resources which brought us to these color coding schemes obviously are not sustainable on the long run. And the way forward definitely is in envisioning a new world, remake world, where the resources from one system would become, of a waste from one system would become a resource for another one, what Cradle to Cradle and Michael Brangard introduced also like 15, 20 years ago as a Cradle to Cradle concept. But it definitely has to be pushed further to the and be taken into account when producing all products from cars to cities. So when we zoom into a construction and the way how we build, the vision which we have here in Europe is definitely that this previous slide is a kind of a priority that we want to go. The circular economy is number one on top of the list of the European Commission's policies in the future. But there is a long way to go when we look at the construction. Obviously, these kind of images and actually the numbers you see here on this slide are not very promising, and it is very difficult. We are still very slowly moving away from these numbers, and they're very much related to the way how we built, and we are still building, unfortunately, our structures. We build them as a kind of static products, which are designed for one use, of one use scenario. And once the use scenario is not working, or there's a new requirement on use, or there's a new idea on city development, we start demolishing buildings because they cannot be deconstructed. The materials are brought together in a way that they are, first of all, composites, so the materials and components themselves cannot be recycled in a mono-recycling way, let's say. But also the parts are also put together in a kind of way of static structures, which enable us to approach selective deconstruction and reuse of its parts. So mainly from economic reasons to start with, the tendency is to demolish buildings because it is much cheaper than employ a lot of labor on this very labor-intensive deconstruction processes. But obviously, this results in a huge CO2 emissions, material resources being lost, and waste production going up. As Mauricio mentioned, couple of years ago, it's already 7-8 years ago, I was one of the initiators of European project Buildings as Material Banks, aiming to bring this urgency and discussion on how do we move further in design of buildings, how do we define the whole system, and how the stakeholders need to act within this new system of circularity and circular economy in construction, where it became very obvious that in order to move further, we need to start seeing buildings as material banks and develop and enable materials to stream through different feedback loops, material feedback loops through their life cycle. And that can be done only by new approach in a design. So this new design task would be to unlock the multi-layered capacity of buildings by understanding and identifying the 3 key dimensions of transformations that every building has, and basically unlocking the capacity of each of these dimensions, being a spatial transformation level, the structural transformation level, and material transformation level. And this concept of three-dimensional transformation within buildings is heavily supported by the way how buildings put together, and definitely design for disassembly is playing a very important role in achieving the full circularity and the three-dimensional transformation. Then brings us to the notion of this new generation of buildings, which is this reversible building. And it brings, the reversible building brings a new paradigm shift to the construction, new perception on buildings, and moving away from understanding building as a static product and static structure, and moving towards more understanding and seeing building as a dynamic structure whose parts can be exchangeable, replaceable, which are upgradable to different functions, but also whose spaces and a building level is adaptable to meet different user requirements. And in order to do that, those are the 3 layers, 3 future, let's say, transformation capacity dimensions, which enables building and building materials to live longer and be used longer. So these 3 dimensions, just to mention them and list them separately, deal with adaptability of space and actually ability of building to accommodate its major structure and a space to meet different requirements. The second dimension, which is dealing with reconfiguration of a structure, meaning that the systems of components of the building as a facades or modules are reconfigurable. The different functionalities to these systems could be brought in or can be changed if the position of the systems is changed or the requirements for them emerges. And the third dimension of material reversibility is everything about separability of materials, so that they can be, in the end, they can go through the mono recycling processes, which is again creating high value materials for future construction. These 3 dimensions together form a basic triangle of a reversible building, which has 2 major pillars: adaptability and reuse, supported by disassembly. And that was for me kind of starting framework for everything I've been working on in the last 20 years. By defining this framework, it became possible to get better understanding of the performance of buildings, to develop also tools, but also the design protocols for design of such buildings, but the tools enabling us to understand the performance and reversibility and circularity of buildings, and cluster and systematize all buildings into three major groups: irreversible, partly reversible, and reversible structures. I'll come later on in my presentation on these tools and tell you definitely much more about that. But to start with, of course, when we want to go and make these big steps to a new world, definitely very different from existing one in terms of how we treat materials and how we build buildings, it is very wise to try to understand the full capacity of the existing buildings. And that's what we've done on a project in south of the Netherlands, where the exercise was about literally decomposing a 10-story building, apartment block, and trying to reuse all of its parts in construction of 3 new houses, and actually understand the processes behind that. Of course, the cost issues, but techniques to deconstruct and also techniques to build new ones, just to understand really what is the capacity of the buildings that we have around us. And in the Netherlands, there are many of these kind of blocks built, especially in 70s and 80s, and big portion of the housing stock is made in such a way. So different recycling and reuse strategies have been tested, starting from creating recycling aggregates from existing concrete to crushing parts of concrete into creating bigger chunks of concrete and using that as a facade, for example. Going to the really cutting of 3D units with the aim to reuse the structural parts to build this new structure for new houses. At the same time, also the reuse of insulation has been tested, cutting of brick facade in smaller blocks, also cutting of some inner partitions of light concrete walls, on-site recycling and construction of recycling concrete has been done, and resulted into construction of these 3 houses, which have been built. This 95% of materials from the donor building, which was standing next door. And this number of techniques have been tested there. Of course, as I mentioned, this has been used to try to understand the impacts of these kind of processes on the environment and economy. And obviously, we did figure out that some techniques, actually many techniques, but for example, the cutting one, if we compare it on the cost side, that exercise was like 10 times more expensive than making just a normal load-bearing structure out of the resources of new concrete. And on the environmental side, as a CO2 concerns, there were not much savings because lots of machinery had to be applied, transport and so forth. So that was tricky as well. But all in all, we did figure out that there are significant savings in terms of reusing of materials. So 95% of materials were literally brought into new houses. Also, a significant amount of CO2 has been reused and embodied energy, but on the cost side, on average, the construction of these 3 houses was 2.5 times more expensive. And it, as I mentioned, it had very much to do with the processes around recovering, which were very complex, involving 5 to 6 different stakeholders, involving creation of new platforms, transport platforms, and so forth. So that all actually is illustrating how complex it is to go to high-value recovery of existing buildings. On these lessons learned, then the idea was to use the good positive parts that we learned through the projects and try to build another 15 houses. And what has been done then, of course, realizing how important it is to create kind of reversible structures where you can recover elements and reuse them again and easily recover this, not with kind of heavy processes around. The new products were developed, as you see here in the upper left corner, for recycled concrete, kind of new shaped concrete block for the wall structure, or the brick, dismantleable brick system for the facade of new houses. And obviously that would bring significant improvements in the costs, and did bring improvements in the costs. Although these new 15 houses were quite simple, but cost-wise, the difference was much. So the new 15 houses were built with lessons learned, and the idea was to try to create as much as possible reversible houses, improving some existing systems on the connection side so that they are easily dismantleable, and trying to fit into the financial framework of the housing corporation. So it was promising, but we are definitely still not there. But the direction was quite clear. Based on this quite heavy exercise, which took place for 3 years, number of reports, you can find number of reports on URA sites. I wrote, I think, about 5 journals. I'm now writing the final one on the final lessons learned. So you can find there lots of concrete data as a result of this exercise. But I also use that to provide kind of recommendations also to the policymakers in Europe on the next steps and what are the biggest barriers we see these days on the implementation of the circularity. Of course, we have to look into the position of the stakeholders and the fact that this conventional supply chain is not applicable. We saw that the stakeholders in the design, construct, deconstruct process are shifting in these kind of circular projects. But most importantly, the focus is on how do we basically enable provide new economic boosts and create economies that will support the circularity in construction, because it was obvious that circular economy does not exist at all, and that the existing regulations are not supporting circular construction. So there are some things that are in preparation at the moment in a number of states and on European level. But the biggest impact definitely can be reached by designing new buildings with higher reversibility rate, which also very clearly came out of this big experiment. So that brings me to the new generation of buildings that, of course, I like to talk about most, not just looking into what has been done, because it is obvious that things were not really done properly or from today's perspective. But let's go to the future and see what can be done to improve the situation for the future generations and to become smarter on how we build buildings and create cities. This is the basic scheme of what reversible buildings, future buildings are. And they have these two, as all buildings, two key elements, as all buildings have: a spatial one, which is then reversible, and technical, aspects, which are in this case also reversible. And as I mentioned in my previous schemes, this concept relies very much on adaptability, on reconfigurability of the structure, and separability of materials. Through the Buildings and Material Banks project, I managed to set up this whole toolkit, which enables future users or the ones who really want to take this path to first design buildings with following the design guidelines and principles, but also measure their performance and use the tools during the design and after the design process to assess reversibility on the technical level and on spatial level. I do hear some background noise, so I don't know if that's okay, it's fine now. So this reversible building design kit, toolkit, as I mentioned, it has 3 components: design support on one hand side, the guidelines, and the tools to measure technical reversibility and spatial reversibility. The tools which measure technical and spatial reversibility are Excel-based and BIM-based, and I will be talking more later on about the technical reversibility and the Excel-based and in particular BIM-based tool. But before that, I'll also, of course, tell you something about the design guidelines, which are on the background of this tool. The reuse potential tool looks into the dependencies that elements have within the building and measures how easy it is to take an element out without affecting or damaging element itself and the surrounding elements. I'll come back to that later on. And it results in a number and a score between 0.1 and 0.09. And transformation capacity tool looks into ability of building, a capacity of building to change the function or adopt different functions without, again, demolishing parts of the structure or the whole structure. Just the level of the core capacity is being taken into account is one of the indicator. The capacity, which also takes into account the space for installation of future installation services and distribution of installations. The disassembly capacity on the building level, this it's mainly about separation of major building functions. The position of the core elements and fixed parts of the building structure, which will provide the space for the future changes, and dimensions of the block, the major block, in the height and the width, which have a capacity for different functional configurations. So those are 4 key indicators that are being calculated and have 16 sub-indicators, but I will not be talking about this one today. And the design process, as sketched here, actually this slide is just mainly to give you an understanding on in which part of the design process, which of these tools is has a priority. And obviously in the preliminary design phase, the transformation capacity indicators are playing important role. And as we move towards the definitive design and technical design, the technical aspects of reversibility with their 8 indicators are then important to look at. Number of these guidelines and definition of indicators and so forth can be found in these documents on the BAM website and on the European Commission's website. The principles for building design have been, which I didn't show them yet, are integrated into circular economy principles by European Commission. So I will now talk more about this technical reversibility and what is being measured to assess reversibility and reuse potential of building parts, and how these indicators are integrated into BIM to get a better understanding and to speed up actually the process. But how these results on the reversibility also help us to identify circularity profiles and index of the building, which also gives us better understanding of the capacity of a building, circularity capacity once it's built, and what can be done in the future with these materials. But this approach is also used on the existing buildings to understand better the capacity of existing buildings and what can be done with the materials within existing buildings before they are demolished. So as I mentioned, technical reversibility is assessing the dependencies between building parts, and which, when you want to really assess these dependencies and understand how easy can you take something out without demolition or damaging, there are three types of dependencies that need to be understood. And these three domains are actually very generic and applicable for all products that we as humans are designing and using, being cars, computers, or houses or systems. And those are all products, whether high level scale as a building or a computer, have the same way of creating structures, and materials in all products have functions. And what we need to understand is how the dependency between different functions are actually identified, and how easy can these functions be independently recognized. Once the functions, of course, need to be materialized. Very often, in order to materialize one function, we need to apply number of components or materials, and that's when the technical composition starts emerges. Technical creation of relational diagrams start to emerge when we start bringing materials which need to support certain functions. The hierarchy of the structure emerges and defines basically the physical structure of the product. And each all the products in materials in a product need to have physical relations very often, and they are then defined by the connections. So the three major dependencies which are addressed by this tool, which measure reuse potential, looks into this functional independency, technical independency of parts, and physical independency of parts. As I mentioned, these three dependencies that are measured, they are important to understand independency and exchangeability of building elements. And in order to do that, 8 indicators have been identified. And I will go through each of them just very shortly, just to give you an indication of what indicators are that need to be taken into account when measuring reversibility and reuse potential. And as I mentioned, one of the first one is the functional dependency and independency, looking into integration of maybe 2 functions into one element or not, and the interaction between different functions, which is very much present also in, for example, interaction between installation services and load-bearing structure. The relational diagrams, as I mentioned, which emerge once we start creating configurations and structuring elements in sometimes different functional groups or not. But what you see here on the left-hand side in the upper corner, unstructured relational diagrams are typical of the way buildings are built now, where it is very difficult to identify any system in these relations, and that's why buildings are being demolished. These are different patterns of relational diagrams. And of course, we want to move more to the lower level, which is more open hierarchical diagram with structured parts or clustered according to their functionalities. The base element is also a very important indicator, which helps us to take one element out without affecting the other one. And this base element is present on different levels of the building. Also, the assembly or disassembly sequences will affect also the ease of taking something out, but also damaging or not damaging during the process. And geometry of component edge, also a very important indicator, especially when considering the damage that can occur based on the geometry that is applied. And the standardization of product edge is also something that helps to speed up the construction and deconstruction process. The type of connections, there are 11 types of connections which I identified so far and using this in these tools from reversible to irreversible. And this is how basically the analysis look like when you start manually to try to understand and figure out how reversible structure is. Basically, I did this for a long time manually, literally just drawing these relations, identifying functional clusters, which belongs to which function and the types of connections. And once all indicators are analyzed and scored, net graph emerges, which is very helpful for the designers to understand which indicator can be improved during the design process if you want to increase your circularity and reversibility of the product. But on the other hand, these indicators are used to calculate reuse potential of the product itself. And the reuse potential score reflects the reuse options of this element in the end. And at the same time, it reflects environmental and economic impact of the operation because it measures how easy it is to take something out without damaging and also to bring it back in a new cycle of construction. That means that the energy, the transportation you need to recover element, repair it and bring it back is being taken into account, and that is reflected in environmental and economic impacts, which is related to the score. So once again, when you start manually to assess, this is a part of Excel-based assessment of reuse potential, then this functional decomposition and technical decomposition matrix is created. And on the horizontal line, when you move horizontally, you will see different functions that elements have. Each element is being placed in the column of its function. And vertically, the assembly sequences are addressed. So the element is placed in the sequence when it's being assembled, so that the dependencies in assembly are also analyzed, and how many steps you need to take out in order to take something out is being taken into account. And that's translated into the matrix that then systematically actually illustrates when which element is assembled with what type of connection. And this is kind of base for the calculation in Excel, which results with reuse potential score on a building level, where we calculate the reuse potential of all elements that are brought to the building site. Reuse potential score on a system level is calculation of all elements within, for example, facade system. And the reuse potential on the product level is a reuse potential of all elements within a window, for example. As I mentioned, the reuse potential score is linked to the reuse options and helps to categorize then the results into these three categories, or identify the category that the building system or product belongs to. And once again, it reflects this, the effort needed to bring back material into a reuse cycle or use cycle again. And the shorter reuse feedback loop is, the less effort you need to bring material element back. And that's why the elements which have direct reuse would score higher with 0.9, for example, 0.8, or elements which have to be crashed down and recycled. They will go back to the beginning, start of the product life. It means in a recycling facility, that means that the feedback loop is much higher and bigger, and much more effort and energy need to be put into this recycling process. And that's why the impact of this process from environmental economic point of view will also be very high. And in reuse potential scoring, it will be 0.1 or 0.02, just to give you an idea how that works. And this helps to, as I mentioned, bring the understanding on the circularity profiles of the building. And in this scheme, I also introduced a transformation capacity part, because of course, the best thing is not to demolish at all. This reuse building, and a building that can be reused would have high reuse, high transformation capacity. So this circularity profile provides some kind of ambition ladder towards circular buildings, which is then used to also in the procurement phases, push your ambition towards which circularity level you want to achieve. So I was talking about this manual assessment of reversibility and reuse potential, and obviously you can understand that it takes lots of time to do this manual work, and that's why at a certain point I decided to try to speed it up with integration into BIM and see whether that will work. And this BIM, I call it Reversible Bim. And this has been tested also on the existing buildings, where we would gather the information from the existing building, do the 3D scanning and create point cloud files of the existing building, and then map drawings with the point cloud files, and then create Reversible Bim, add the plugins that I will show later on, do reporting, and that is working unexpectedly well, actually. This is an example of a 3-point cloud file of the museum in south of the Netherlands, which will be deconstructed at the end of this year. It's a Roman museum. So after scanning, the model was created, and as you understood in my previous slides, we need to be able to analyze the relations between all elements. So it is very important to build a BIM model where you can identify all elements and also analyze interactions between the elements. So there is a reversible BIM protocol which is put in place for the ones who want to use BIM model to assess reversibility and reuse potential. Then modeling needs to take into account these features. Later on, the materials are added. They use ICE database in order to calculate also CO2, avoided CO2. But I also added the technical life cycle database from the Netherlands, because a model measures remaining technical life of the parts. The part which was quite difficult, and that was to assess the technical life cycle of materials of all the buildings or monuments which are not in the technical database of new materials. So I managed to set up a list based on the talks with the experts in renovations and architects working in a renovation of monuments, just to have a start on that point as well. So once that is done, then based on the classification of connections, for example, which I also showed, the connections are assigned to all elements. Of course, parts which have the same connections can be selected at the same time to speed up, and the information on how many connections which element has and what type of connections is there. Also, the hazardous connections, as you see here, D1H would mean, number H would mean that there is a hazardous component in this connection, and asbestos, for example, and that information is also taken into equation when assessing the use potential in the end. And as an output, there are different types of outputs, but just to give you an idea how complex buildings are and how this digitalization helps us to get a better understanding of the complexities. This is a list of a couple of elements and number of connections they have, and you will see here that majority of elements have multiple connections and also different types of connections. And there's also difference in connections, what I call connections to and connections from. When we assemble an element, we create a couple of connections to assemble one element, but once element is assembled, another connections are created with that element to assemble other elements. So there is this distinction, which is also important when, of course, I want to assess dependency of these elements. And this is the Excel, now the matrix, which I showed in the beginning, and you see here in a small scale in a corner, which was done in Excel. Another slide just to give you an impression of the complexity that buildings have in themselves, and again, how this BIM helps us to go and look through it. Is the relational diagrams, and these ones are now automated, and you can imagine that in this museum, we identified 7,277 elements, and the color coding here is related to the number of relations that these elements have, and elements which have up to 5 connections are green, and more than 10 red. But here we also identify 36 parallel assembly and disassembly procedures. So that helps the construction companies to understand the process of the construction, for example, as well. So indicators which I was talking about in the previous slides when explaining the manual assessment are integrated into a BIM. And in the end, when all parameters are put into a model, one of the outputs is a color coding. And this color coding is actually expressing the reversibility and reuse potential of individual elements. At the same time, we get lots of outputs which you can expect from BIM on a type of element, its functionality, but also the volume, the embodied carbon, the use potential per element, and then avoided carbon and avoided volume, which is based on the reuse potential of the element. A nice thing is that there's gradation of data that can be shared with different stakeholders. And this is a graph, for example, which users and owners of the buildings are quite interested in, a kind of helicopter view on what materials I have in a building, the percentages of tonnages and of different materials in a building, then the reuse potential category of a building, and the CO2, how much can be avoided, and the tonnages per function if you want to do something with the enclosing or a facade. You know that, for example, in this building, 55% of all materials are in a facade, and that 63% of CO2 is embodied in that facade. So it's kind of helicopter view. You can also zoom in on each individual material, which is then also structured along the reuse options that materials have, so that you can assess the reuse potential, grading, and a score of individual material, which can be handy for industry or for the construction companies. And also, this is an overview of different reuse options. There's materials in different structured along the line of reuse options. And here we see mapping of embodied material, for example, in tonnages, and what can be literally reused out of this material, because during the reconfiguration or recovery process, you will always lose some materials. Depending on the reuse option, the material is, you will lose different amounts of materials, and that will be reflected on a carbon as well. So there is an embodied carbon in a building, but depending on the reuse scale, the reuse stage of the or option of material, carbon will be lost in some percentages. And that's also being illustrated here. What's also interesting to look at is, this is material versus carbon, is that, for example, concrete has lots of tones. It's a very heavy material. So its contribution to the waste when we look into tonnages is very high, but when we look into CO2, it's very low. Steel, on the other hand, is, like in this case, less heavy than a concrete, but its contribution in CO2 is much, much higher than, for example, concrete. So these kind of comparisons between materials, their contribution to the tonnages of waste or versus contribution to the CO2 is also quite interesting to look at. I'll just run through this. This is an additional output, which is very often used by inventory companies doing inventory. So there is an inventory data which you can get on a building level, just giving the total amount of materials, carbon, number of products, average reuse potential, and then it can be split into the functional parts like facades, equipment, finishing, with the same amounts. This going back per different functional groups, again, volume, carbon, material, and then the functional groups can be split further to their parts, systems, components, and that can be also split further. I didn't include that one just to spare you some time. Sorry. Once these analyses are done, then what we also do is identify elements which have high reuse potential, and then create BIM objects. And this is an example of BIM objects of steel profiles from this museum, which these files are shared with the Janssen producer. It's one of the biggest steel facade producers in Europe. And they have also created these profiles in the 70s. So they have produced these profiles for this project, and they found it in their archive in 1970. And they still use similar profiles. So we have shared the BIM objects so that they have included them into their digital library and their harvest maps, where they then also purchase these materials for use in a new construction. But these BIM objects of reusable materials definitely, I think, will be in the future catalogs of materials that architects can use when designing new buildings, which will speed up use of reusable parts in new products. So now going back to the assessment models and circularity profiles, what that can mean, it helps us to understand, for example, in this case, the economic impact of different types of construction, where here you'll see the green line would be kind of reversible building in housing. This is in the scenarios for housing in the Netherlands, how often they are being built, rebuilt, or demolished, and so forth, the total life cycle of 50 years. So if you do it in a reversible way, or in different scenarios of reversibility, what would be the total costs of that operation? But this total life cycle costing of an operation is being looked at on an energy level, on CO2 level, on a waste level, and so forth, and helps us. This is developed for the region of south of the Netherlands, based on their predictions of how many buildings they need to demolish in coming 10 years and how many need to be built again. Understanding the type of economy that can emerge when building one or other circularity profile in the future. Talking about digitalization, the reversible BIM module is then integrated in digital construction platform that Maurizio mentioned we are working on now. It is also a European project where we are bringing 4 modules together on a digital construction platform that will help decision makers to make a decision on strategies on the construction and the reuse of materials. So we bring together 3D scanning module, reversible BIM module, digital database, which is then linked with blockchain linked to the sales platform. And the idea is how these modules work. This basically, I did mention that shortly. We scan a building, create a reversible BIM out of a building, and then the material list of reusable parts are created and connected with the sales platform. The platform itself is being developed by LIST, that's an institute in Luxembourg, and they are putting these modules together. And the idea is that through one, you get one-stop shop, let's say, as owner of a building, with all your data on a building, with respect to the materials in it, its status, what cost benefits analysis that need to be made in order to understand better which decisions can be made with respect to one or another, the construction or reuse strategy. I mentioned a couple of things, and obviously this is not this transition that we are talking about is not something that will happen tomorrow. I've been working on this for more than 20 years. And in this period, it was very clear to me that we need really to be very systematic and go step by step. That is also the reason why I initiated a couple of hubs and labs in Europe. This is one in the Netherlands, the Laboratory for Green Transformable Building, which is under construction right now. And the aim of this Laboratory for Green Transformable Buildings is on one hand side to demonstrate that we can build buildings which can reduce the waste CO2. It is on one hand side a demonstrator of the ways how the buildings can be designed and what kind of conditions are needed to develop new products and reversible buildings. And on the other hand side, the aim of the platform is also to establish this monitoring and scoring system and help with standardization of the quality of circular buildings, and also do the established monitoring system on a city level, where we will be capturing information material streams through the city and help develop the infrastructure and identify the infrastructure that is needed to support the circularity of materials for new construction. So in terms of demonstration, this has been done and tested previously, and some parts are now also brought back into construction of the lab. This indicating, now you will recognize some things here as geometry of product edge, for example, here, reconfigurability of parts, or maybe go back here. What you see here is the facade in the facade, floor, and the ceiling, and they are all the same, standardized, prefabricated parts, but they are also reconfigurable, meaning that you can make a window in them, or an opening, or a door. That is what I mean by reconfiguration when talking about that part, that dimension of transformation. We also support this development of new products, which will enable reversibility as these base elements I was mentioning. This is a production line at Janssen, where we are trying to develop the new profiles that will enable easier the recovery of building parts. Now, I have also established a center in Southeast Europe in Mostar, which is called Green Design Center, where we are actually using the existing structure, and you'll see it here on the right, lower right corner, the existing military barrack, which was built by Austro-Hungarian army in 19th century. And we did not demolish it. Also, the city thought we should. And we basically reused the robustness of this structure to develop kind of reversible, again, approach to adding modules, reversible modules, which can help to create flexible and transformable structures inside. So that's another experiment which is happening in Southeast Europe, and this lab in the Netherlands and Southeast Europe are connected and try to spread out the word on this issue of circularity in different regions of Europe. In order to share the knowledge, at the moment, I'm also working on 2 other platforms. This is an ICT knowledge platform for circular buildings. This will be launched after summer, where the guidelines, policies, toolkits, but also exemplary construction products, materials, building materials and systems will be on the platform, and there will be European-based, this mainly information from European countries will be there, but we might extend it to other countries as well. And circularity meter, this CT meter of material streams will be on that platform as well. And there's another one, the Reversible Building Design platform, where this much of what I was talking about, the design principles, but also projects, instruments, and the Circularity Index will be on that platform, with projects as a reversible building projects and their results on the reuse potential, also the light version. So we are working also on the light version for calculation of reuse potential for the ones who do not find Excel very complex, which is complex, then to use this light version for the calculation, and the reversible building design guidelines will be there as well. I think this is my last slide. Yes.
Well, here is the full screen of the certificate that we will send to you, to your email. And again, thank you very much for your participation, for your contribution. It's very, very, very nice. And thank you, everyone. Thank you to the audience.